All right, we are back at it with another codebook walkthrough. I'm going through there's a branch here. If you remember last time we finished the introductory section. Now there's a branch to algorithms and Hamiltonians. I'm just going to go to algorithms. Not for any particular reason, but just seems like a shorter one to go through. So I'll just do that one first. But of course, we will eventually do Hamiltonians. So as usual, we just get right into it. We have our code that we're just going to be going through sort of live without preparation. And yeah, that's pretty much it. So let's just get right into it. All right. Once again, once it gets to a point, probably in like the Hamiltonian simulations where I can't just think about this and solve the problems, I'll have to actually read and go through this stuff. But for now, this is pretty basic stuff, so it's really more of a question of how to do it in penny lane than it is a question of how to do it at all. So in fact, I didn't even read the problem. I'm sort of just, I guess this is a holdover from when I used to do those, high school quiz contests or whatever, that I'm optimizing this for speed, trying to get the answer as quickly as possible. So I figured this figure is probably what we are going to create. And you'll probably hear a lot of clicking. That's my keyboard. If it's annoying, you let me know and I can probably try and do something about it. I didn't have my keyboard attached before, and that's why it wasn't. That's why it's a new sound. But yeah, anyway, we're getting right into it. Let's hope. Yeah, I was hoping that would be right, and we got it. Creating our equal superposition. I should zoom in over here. Ooh, I like that lesson. That was an easy one. Okay, now we got our magic 8-ball, also known as an oracle function. All right. Okay, I should actually read this. Write a function that returns the oracle in matrix for a secret given combination. Okay, what the? A list of bits representing a secret combination. Index. Wait, I don't understand what this lock is doing. Oh, okay. So this is basically Grover's or not Grover's, what's it called? Simon's, or is it Dutch? I don't know. There's so many. I don't know. I-2. Yeah, this is just okay. Anyway, I'm getting sidetracked. What we want to do is flip the sign of the bit or of the state that corresponds to yeah, this is setting up for Grover's. For one situation, this is true. For everything else, it's false. And for that one situation, we want to flip a sign. So this is just Grover's oracle, basically. And if you remember, I actually did an extensive video on basically just this oracle and the operators around it. So you can check that out. So let's hope this is easy, right? So we have our identity minus the outer product of the desired states. So we have our states, so we can do combo equals, I'm just changing this to an array, and then we're going to say my array equals my, because this is the identity, minus 2 times the outer product of these two states. And that's just a formula that we have given right there. And that's not right. Oh, it's the combo index of the solution. Oh, should this be index then? I guess a combo. What is going on? I need to look at these. And it doesn't work. Let's see, can I do print, I call it down here, Oracle matrix n. Now let's see if we can do print combo. Oh, I have to, oh, there it is. Print array. Yeah, so that's why. So this is the secret, right, combination. That we want. Oh, this is so annoying. Why can we not just... So if... Yeah, the problem is the matrices aren't the same size. Sorry, I need to focus more on thinking out loud. So the problem right here is that the matrices, right, this is a 2 to the length of combo by 2 to the length of combo. So in this case, combo is, let's do 2. So this is a 4 by 4 matrix, whereas the outer product is a 2 by 2 matrix. Because it isn't, combo isn't actually the state vector. It's a list of bits representing the secret combination, which seems like it should be the same. Oh. Which seems like... No, I'm confused as to what this... Yeah, like I get what the Oracle does, and I get what the whole purpose is, but I'm confused as to this lock. Why are they using this? Yeah. Yeah, okay, that's fine. Like I'm confused what the combo is. I thought the combo would be, right, the thing that opens the lock is this S state, which is some binary string, right? It's the 001 state or whatever, right? But it seems to be bits rather than... Yeah, okay, I get what's going on here. Okay, I see. So the thing I was just confused about is the dimensionality of this. So this is a... Combo is S, but S refers to a specific index. So what we want, I see. What we want is we want we want to make this. So this will be, this is just a 0 array that represents basically our state, and then we want to do test index 1. Now let's see if this generates the correct, yeah. So the problem was I was just getting confused by was that combo here is not the like state vector, it's just the set of bits. So it's just one of the states, but there's 2 to the n possible states. So we evaluate those 2 to the n, and then we do the outer product, right? I thought what they were handing us was this array right here, rather than this combo. But I don't know how the next one is going to be Grover's. This is all like Grover's algorithm right here. I'm kind of curious just to look at this. Oh well, there's the answer right there, but anyway. All right, looking ahead. write a circuit that applies the oracle to the uniform superposition. Okay. And bits we want to range and bits we want to do the pattern mark on I, and then we want to do qubit unitary onto the oracle matrix combo. Oh, right, I have to do wires equals n I range and bits. There we go. So right, we just make the Hadamard and apply the qubit unitary. Oh, wow, this is going so quickly. Actually, let me check the recording. I'd be so sad if this was not actually recording, but it is. 11 minutes, 11 seconds, so we might actually just be able to knock out all of A. This is going so much quicker. I thought it would be. Okay, let's see. Oracle adds a simple phase. Doesn't change the probability, but it changes the relative phase. Wow. All right. Implement this circuit right here and return the probabilities. Yeah, their one is so much prettier, but that's okay. All right. All right, so they've implemented that for us. So we want to do what we want to do is qml dot Hadamard is equals n bits minus 1. It's the last one. We want to do the qml dot qubit unitary. Right. We want to do oracle matrix combo, same as before. Wires equals I for I and range and bits. There's probably an easier way to do this. And then we want to do another Hadamard wires equals n bits plus 1. All right, perfect. So now we want to see how long it'll take to brute force this. All right, complete a function below that sees how many attempts it takes to break our lock. You should see an improvement from 9 guesses, which is good, which is roughly half, right? There's 4 qubits, so there's 2 to the end possible locks. So there's 2 to the 4, which is 16. So we're going to get on average 8 or 9, guesses before we get the lock, because it's going to be halfway through, assuming the lock is, a uniform random picked. But now we're saying, oh, we can do twice as fast. So let's see. We want to do we'll be in state 1. So we want to do E equals Q pair circuit X for the combo. And then we want to say if P, if numpy is close Let's see if this is correct. Might take a little bit if they're doing. Yeah, so what am I doing here? I'm saying P is, right, the probability, so it's going to be probability of state 0, probability of state 1, and state 1 means we're right, so we care if the probability of state 1 is close to 1, and it's right. All right, now we are, I like these titles, Making and Breaking Promises. It's pretty literary title right there. So, all right. Now implement the circuit above, but now for how many solutions instead of one? We'll first need to implement the multi-solution. Oh my god. Which takes a list of bit strings and returns the associated oracle in matrix form. All right, I will use the advanced technique. I'm gonna do this right here. Copy this, and then we're gonna go over here. We're gonna say for I in indices, my array of I equals -1. Now we return my array. All right. And then we say ml.Hadamard wires equals n bits -1 qml dot, what is this, multi-sol, or really not a great function name. I mean, it is because it's informative, but I don't like typing it. Hadamard wires equals n bits -1. All right. Combos. I mistyped combos somewhere. Combos. There we go. Index 12. Is n bits not it anymore? Oh, no, it is. Oh, whoopsies. Combos at 0. There we go. Okay, probability distribution does not look quite right. Really should have been. Let me double check what this. Oh, I just didn't apply the qubit unitary for some reason. I don't know what's going on there. N bits. All right. 10 valid syntax, line 43. I probably forgot to put a parenthesis right there. There we go. That's all I had to do. Now we want to create a routine for checking the parity of our locks. We want to say, we want to do, copy this. So the state counts the number of solutions. So if we do n bits x tilde. Oh, I see here the combos here. So now we do P0, P1. This might be more informative. Okay, now we want to set the parity of the solution set. The parity of the solution is the number of solutions. So we want P1 plus P1, P1 plus P1, P1 equals P1 plus 2. What are the odds that's right? All right. E equals. What are the odds this is right? No, it's not. Okay, so the state counts the number of solutions. Parity. So if it's even or odd. Oh. Do. Oh, I see. If a single solution is present in the last qubit. So we want to say, oh no, that's still right. So if qubit 1 is in state, or if the qubit is in state 1, it's the number of, maybe I don't need this mod 2. Okay, I don't understand what they want me to do here. Checking the parity. Okay, maybe I just need to look at, I know parity is the number of even or odd solutions, right? So if even, okay, so we have our guesses and our combos. Oh, that's why I should do parity. That's just a simple, I'm pretty sure. Can't spell. So, oh, why? Okay, let me think. Here's the first encounter. Maybe I will actually read this. On single solutions, but what happens for multiple solutions? Not all hope is lost if there's an odd number of solutions. Oh, I see. I see what I'm doing wrong. I see. So if we can tally up the number of times we detect one. Parity. There we go. That's what. So basically we count the number of times we think we find a solution, and then we can return the answer. Okay. All right. Let's see if I can finish this out. 24 minutes. Maybe I can do this super quick. All right, so now we can do Hadamard, right? Because that's like trying, I don't want to be that guy, but that's like trying all possible, right? That's a superposition, so it's all possible states. So now what we want to do is say, implement the circuit above. Oops. There's y. So now we do that. Okay. So we want to do qml.qubit unitary, and we want to do combo oracle matrix combo wires equals I and range and bits, right? I do not know. It says use the broadcast function. Okay, so we want to do broadcast unitary wires pattern. So we want to do unitary qml.pattern wires is. I really wish they gave an example with these. Oh, their docs are so annoying. Like, see, qml.broadcast, like, okay, I can sort of see what it does, but oh, they do provide one. Okay, that's on me. I admit it. That one's on me. I apologize. I was being very annoyed that this was not existing, but it's okay now. Wires, okay. This really doesn't seem like it helps me at all. I'm literally just writing out the exact same, like, for I in range and bits. Like, I feel like, okay, I actually have to check this now. And I'm not even, so this is, oh, I'm not gonna, let's see if it lets me do this. Hold on. Wires. Okay. This is gonna be wrong. I just want to see. Oh, is it qml.broadcast? Yeah. Okay, yeah, so this is a valid thing. So I'm just gonna check. Okay, I'll just do this. Okay, so this is 65 characters. Now if I did this, this really is not related. I'm just invested in doing this. It's wires I. Okay, this is also valid. I'm just checking to make sure this is the right. Oh my god. I thought it was gonna be like that. They're literally making you write out more. This is longer. This is more complex to write and also less intuitive than this is. Okay, I'm not saying broadcast is not a useful function. I'm just saying why is this their teach case when it's not helpful? Literally more work. So no, I don't want to use this. Oh, unexpected indent. There we go. Look at that. Perfect. And I didn't use broadcast because it's easier not to. That's funny. All right. Finished that lesson. Oh, now we're talking about the Deutsch-Jozsa algorithm. I swear, every time I've said this, I say it a different way. I'm not going to talk about too much about this algorithm. I was planning on making, sort of continuing my intro series with it, so I don't want to spoil too much about it, but sort of like walking through it. But here we go. Implement the circuit for this. Implement the circuit above for the set of solutions. All right. As before, you are given this, so we can do qubit unitary this thing. I for I and range and bits. All right, now what is different? Oh, just submit. Ooh, there's another very clear patterns here. I'm not going to talk about those patterns because I don't want to spoil too much about it. All right, let's look at this. Implement the algorithm. Given a constant or balanced function promise var flag. Oh. Given, implement the circuit from above and determine which it is. Okay, so we want to do um, if problems one, or I should do close is close is close. So if there's what we're doing here is nope, it's not right. Wait, what am I even trying to do here? If we measure 0, f is constant. If we don't measure 0, f is balanced. Okay, so we did this function here. Now we want to measure it. Maybe I should do DEPSH 0, and then we want to say all right, let's just debug this a little bit, see what's going on here. So this is a oh, I see. So this should just be the other way around. I think. There we go. I just thought a I just reversed what I thought these were going to be in my head. What is going to be? All right, we finished this. Once again, wow, that was all very impressive. 33 minutes. Once again, I didn't really go into depth. This looks like a good tutorial on the algorithm, but I'm going to make a different sort of discussion of it, so I didn't really do too much. We'll get into Grover's next. And yeah, I think that's everything. Sorry for the flaming of the broadcast. There are a number of examples, so I appreciate that, Penny Lane team. And yeah, I think that's everything.